we're continuing on in our redox unit. We are on to writing half reactions and then putting them back together into redox. So what is a half reaction? Well, it should make sense, it's half, right? Well, in this unit, a half reaction shows oxidation or reduction only. It includes electrons in the equation, which we haven't really written like that before. And it absolutely must show conservation of mass or matter as well as conservation of charge. So to show conservation of mass, the number of atoms must be the same on both sides of the equation. So you can see in this example, I have 1 carbon on the reactant side and I have 1 carbon on the product side. I have 4 hydrogen on the reactant side and 2 times 2 is 4 hydrogen on the product side. And I have 2 times 2, which is 4 oxygen. I have 2 of them here, and then 2 times 1, so 2, and that's 4. But this is another really quick way if you're given mass. So watch this. If I have 16 grams and 2 times 32, that's 64 grams. And I have 44, and 2 times 18 is 36. If I add up 44 and 36, I get 80. If I add up 64 and 16, no big surprise, I get 80. The number of grams should be the same on both sides. All right, to show conservation of charge, if you add up all the charges on both sides, it should be equal. So let's look at why this one is the right one. So this has a charge of 0. This has a charge of -2, and 2 electrons is -2. So -2 and -2 is -4. Well, 0 and -4 absolutely do not balance. This has a charge of 0. This has a charge of -1, and this electron has -1. So that's -2. Let's look at the other one that's not the answer and why. On this side, it's +2. This calcium is 0. Those electrons are -2. So a +2 and a -2 are not the same thing. So this has +7 plus 3 electrons. So I had +7 and then I have -3. So when you add those together, because they're on the same side, see there's the arrow, I get +4. And on the other side, look what I have, +4. So the charge does not have to equal 0 on both sides. It just has to be the same. Remember, the oxidation state of any uncombined element is 0. The oxidation state of an element combined in a polyatomic ion or in a compound is definitely not 0. Remember oxidation versus reduction. One way to remember this is with this saying, Leo says Gur, lose electrons oxidation, gain electrons reduction. Another way, if this is the way you prefer, is oil rig. Oxidation is loss, reduction is gain. Okay, so I prefer the Leo says Gur method, but if you like oil rig better, use that one. Drawing a number line absolutely positively helps. First of all, it helps you determine if it is reduction or if it is oxidation. Okay. Second, if you remember to put these arrows, right, this points to the side you should find the electrons on. This points to the side you should find the electrons on. Genius, genius. Also, it's easy to see when you look at a number line that when you follow oxidation, the oxidation state gets larger because when we go this way, the numbers get bigger. And it's easy to see that when you go this way and follow reduction, the oxidation states get smaller. So remember, electrons go on the product side, the oxidation number increases. Electrons go on the reactant side, and the oxidation number decreases. We can tell oxidation versus reduction by looking at where the electrons are, which is what I just said, right? So which represents reduction? So remember the number line, so you just draw it real quick, okay? So when it is reduction, electrons belong on the reactant side. So see right here, they're on the product side. Product side. Automatically get rid of those. Now I need to see which one correctly represents reduction. So that means I'm going to have to show conservation of mass and charge. Well, in both of the examples left, I have 1 Mn on each side. So charge is going to do it for me. So let's look. I have 4 plus and 3 negative. What would that give me? Positive 1. Is that what I have on this side? It is absolutely not. So hopefully this one works out. So I have positive 4, and then I have 1 electron, so that's negative 1. When I combine those, I get positive 3. Is that what I have on the other side? Absolutely. So this is my answer. Which of the following is a balanced half reaction for the oxidation of copper? So again, remember this. When I have oxidation, my electrons belong on my product side. So here they're on the wrong side. Here they're on the wrong side. Okay, so for my remaining 2 choices, they both have 1 atom of carbon on each side. So conservation of mass won't help me. So charge is what's going to do it. Now, I can tell at quick glance, look at this. This has positive 2, that's a 0, and this is negative 2. Well, that is completely the opposite. So this one better work out. So this is 0, this is plus 2, this is minus 2. Plus 2 and minus 2 is, in fact, 0. All right, also remember this. Whatever is reduced is the oxidizing agent. And whatever is oxidized is the reducing agent. Remember, an agent doesn't actually do the work, but sets it up. So an oxidizing agent doesn't do any work, but it sets up oxidizing by reducing something. And a reducing agent doesn't do anything really, except it sets up reducing. How does it set up reducing? By making sure something gets oxidized. Okay, that was a whole lot going on. So let's look at an example. We're going to look at a redox reaction, one that we actually looked at in a previous video, and we're going to break it apart into half reactions. All right, here we go. So again, we looked at this in a previous video, and we separated out the charges. Remember these right here, SO4, which has the charge of -2, that's something that's a polyatomic ion, and it came from table E. So are there any spectator ions? That's something in a compound on both sides. Yes, there is. So cross them out. There we go. Now we're going to rewrite it without the spectators, because writing a half reaction, we don't want spectators. So here we go. Now let's look at each element separately. We're going to start with zinc. There's the change that zinc had. The change in charge is this. On one side, the charge is 0. On the other side, the charge is +2. Absolutely. Negative, negative, can't be. Why? Conservation of charge. Charge must be conserved, and we can't have 0 on one side and +2 on the other. So let's go back to it. The charge changed. So that means electrons were moving. Electrons will help us balance the charge. So let's go back to the number line. All right, here's our number line. We started at 0. We moved to +2. Okay, so how many spaces did we move on that number line? 2, right? So also going from 0 to +2 shows us LEO, oxidation, loss of electrons. So we need to put the electrons where they belong. But remember, once we follow the number line, this points to us which side the electrons belong on. Okay, so also notice this. When I went from 0 to +2, that goes that way. Do you see? That's the side the electrons belong on. And remember, we said 2 electrons, so we put them there. Well, now the charge is balanced because we have 0 on the reactant side and we have a +2 and a -2 on the product side, but those together add 0. So this is the oxidation half reaction. It shows conservation of mass, 1 zinc, 1 zinc. It shows conservation of charge. So let's go back to our equation and let's look at copper. So this is what copper looks like at first, right? From +2 to 0. The charge on one side is +2. The charge on the other side is 0. Negative, negative. Can't be. Why? Law of conservation of charge. We can't have different charges on both sides of the equation. What do we use to balance the charge? Electrons. Okay, so electrons can help us balance the charge. So let's look at the number line. All right, so we went from +2 to 0. Look at the way that arrow points. Okay, what is it following? What direction is it moving? So, and how many spaces is it moving? So 2 spaces. So that's how many electrons. So it shows reduction, gain of electrons. We got to put the electrons where they belong. But the arrow for GER, also the arrow from the starting charge to the finishing charge, shows us what side we should put the electrons on. Also, in terms of balancing, it should make sense. Okay, so now the charge is balanced. There's a charge of 0 on the product side and a +2 and a -2 equaling 0 on the reactant side. So 0 and 0 is balanced. Already was balanced for mass, 1 atom of copper on each side. So this is the reduction half reaction. Now to make it redox, we're not done. We take the half and put it together. So we take the, which one is this? Reduction, gain, oxidation, loss. We take them and we put them together. But before we do that, we have to ask ourselves a couple questions. Check the number of electrons. Are they the same on both sides, meaning both equations? Well, I have 2 on the reactant side, right, with the reduction, and I have 2 on the product side with the oxidation. Well, yeah, that's the same. So literally just combine the reactants. So you just make it into one reaction. So everything that was before the arrow over here and everything that was before the arrow over here is now all together on this side. And everything after the arrow over here and after the arrow over here is on the other side. Now, notice I didn't write the zeros. I don't really need to write the zeros. You would not get it wrong if you did. Okay, just so you know that. And voila, we have a balanced redox reaction. All right, let's try another. We're going to kind of move it a little faster though. All right, so let's see. Here's our equation. Are there any spectator ions? Do we have something in a compound on both sides? Nope. All right, look for any uncombined elements. Give them an oxidation state of 0. There we go. Determine the oxidation states for all combined elements. So we're going to look at the periodic table and we're going to look up aluminum and we're going to look up oxygen and we're going to put those where they belong. And then we're going to look at a number line to determine oxidation and reduction. So there's our charges, all set. Now we need to figure out oxidation versus reduction. All right, are you ready? So this is what we had. There's our number line. Let's look at aluminum. Well, aluminum changed from 0 to +3. So when we look at that on our number line, that follows oxidation. The electrons belong on the product side because remember from 0 to +3, that's the way the electrons point. So we get this as our half reaction. 3 electrons because we moved 3 spots on the number line. Charge is balanced. Beautiful. Mass is balanced. Beautiful. All right, let's look at oxygen. Oxygen changed from 0 to -2. That shows reduction from 0 to -2, and the electrons belong on the reactant side. But we have to be careful here because we started with O2. So you can see Al was just single, but O is O2. So from 0 to -2, that's 2 electrons. But we started with 2 oxygens because we had an oxygen atom and an oxygen atom bonded together diatomic. So when we write our half reaction, we have to use O2. So like this. So if one oxygen gained 2 electrons, then 2 oxygens together would gain 4. Okay? And when you look at this, then the charge does in fact balance. It's -4 on both sides. So yes, the charge is balanced, and I have 2 oxygens on both sides. So yes, mass is balanced. And now we're going to try and put them together. All right, ready? Here we go. We're putting it together. So there's our reduction, there's our oxidation. Now, I usually write it that way because it's redox, but you don't need to. You can put the reduction one or the oxidation one first. That's irrelevant. Now we're going to get ready to put them together, but before we put them together, we have to check the number of electrons on both sides. So here I have 4, here I have 3. Oh, no, more steps. Okay, so what I need to do is find the least common multiple for the electrons. So I have 4 and I have 3. What's the least common multiple? It's 12. So now what I need to do is take this whole thing and multiply it by 3. And take this whole thing and multiply it by 4, okay? Because I need to get to 12. I need to make the 4 end up being 12, and I need to make the 3 end up being 12. So do that. So on the oxygen side, that's what I'm going to end up with. On the aluminum side, that's what I'm going to end up with. Now, for each of these, I have charge balanced. For oxygen, it's -12 on the reactant side, -12 on the product side. For aluminum, it's 0, and then +12 plus -12, which is 0. Mass is balanced. I have the same number of atoms on both sides. So now I can finally take those and put them together into one equation. There's my redox equation, and voila, I have a balanced redox reaction. All right, let's try one more. So let's see if we can go through it. Okay, so do we have any spectators? Yes, look at this. Oxygen, oxygen. So we can ignore it. Let's look for anything that's not combined. So that gets a 0, that gets a 0. Okay, now we have to figure out the charge of this one and the charge of this one. Okay, so this one I can reverse crisscross. So this is going to be a +3. Okay, and this one, what is it going to be? Well, +4. This is not ionic, so I can't reverse crisscross. How do I know that it's +4? Well, oxygen is -2, and there's 2 of them. So -2 times 2 is -4. So in order to balance out, that would have to be +4. I can only do this reverse crisscross when it's ionic. How do I know it's ionic? That's a metal. Okay, so now I'm just going to real quick draw a little number line. 1, 2, 3. And I'm only going 0 and to +4. I actually don't need any negatives in this number line. This way is Leo, right? Terrible handwriting with the mouse, and this way is Ger. All right, so let's look at iron. Okay, iron went Fe +3 to 0. So it went this way. So I gained electrons. So +3 electrons is Fe with no charge. All right. Now let's look at carbon. Carbon started with 0 and it went to +4. So it goes this way. So carbon +4, and that's 4 electrons. Okay, So mass is balanced, and charge is balanced, but let's check. So I have 3 electrons here and 4 here. No, 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 that does not balance. So what I need to do is take the whole Fe thing and multiply it by 4, take the whole C thing and multiply it by 3, and then I can combine them together. So I'm going to end up with 4 Fe plus 3 plus 12 electrons plus 3C. So do you see how I got that? And then yields on the other side for Fe plus 3C plus 4 plus 12 electrons. Okay, a little slanted because I was writing with a mouse, but there we go. We did it. We got all of the pieces. So this is how you would get there. This is what you would do. When you're writing the oxidation half reaction, you can just write this. This is reduction. And when you're writing the oxidation, you can just write this. When you're writing the full redox, you need to have the number of electrons be the same on both sides of the equation. And there you go. That's the basics of writing half reactions and putting them together to make redox. I hope you learned something new today.